you so much for joining today's webinar. This is the fourth event from our Sterile Filling 101 webinar series, and today we will discuss aseptic filling techniques for highly viscous drug products. The takeaways from today's event will include formulation and filling techniques for viscous filling, how to determine equipment and process requirements for a viscous product, and other considerations of viscous filling, such as non-Newtonian versus Newtonian solutions. Today we have CEO Dr. Shawn Kinney and process engineer Ben Callan to speak. My name is Sarah, and I will be your host for today. Very quickly, we welcome your questions during this presentation. To ask a question, select the arrow that is in the toolbar at the right-hand side of your screen, write in your question, and click send. And now that's out of the way, let's get started. So first, I want to invite Ben at Berkshire Sterile to speak. Ben, can you give us a quick overview of why filling viscous drug products pose a greater challenge than non-viscous solutions?
Hi, Sarah. Absolutely. The greatest challenge with high viscosity drug products is moving the solution. If you have a product that is as viscous as honey, how are you going to move it through tubing effectively? Most drug products filled at BSM are pulled through the tubing using a peristaltic pump. This is a pump that massages soft silicone tubing to physically push solution through, and it also creates a small vacuum to draw in more solution. As the pump moves, it pinches the tubing and rotates, creating a vacuum just behind the pinch. The solution moves in to fill that vacuum. This is very effective for most solutions, but it becomes increasingly challenged for viscous solutions. If you think about how a straw works, you create a vacuum to pull solution through the straw. It works well with water, but if you tried to siphon honey with a straw, it would be much more difficult and would require more time and effort to pull the honey through the straw. Peristaltic pumps don't work very well for viscous solutions, and we typically start to see it become much less effective at around 100 centipoise. We typically move to using a piston pump. Piston pumps are durable and simple. The ones we use at BSM are made of stainless steel, and they come in direct contact with the drug product solution, so they are single use. They consist of a piston, a chamber, and 2 valves. The pump works by driving the piston up to pull in solution through the inlet valve. This creates a stronger vacuum than the peristaltic pump that pulls the product in. Once the piston has reached its maxed height, it will shut the inlet valve and open the outlet valve that leads to the filling needle. This is done by turning the piston like you see here. Next, the piston moves down to physically push the solution out into the outlet valve. The outlet valve is then closed and the inlet is opened, and the process repeats itself to deliver the next pump. The motion is simple, mechanical, and efficient at moving viscous solutions through tubing. We can operate with just a piston pump to move semi-viscous solutions. So, for solutions that are around 100 centipoise to 1000 centipoise, we will fill typically from a glass vessel or a biobag. The tubing leading to the piston will often be cut as short as possible with a large inner diameter to reduce stress, and it will be reinforced to prevent kinking. The tubing leading from the piston pump to the fill needle is rigid tubing, and I will describe why soon. Once we get to more viscous solutions, the vacuum the piston pump pulls is not enough to effectively pull the solution into the pump. Solutions that are at or over 1000 centipoise usually need a push to effectively feed the pump, and that is when we pair the piston pump with a pressure vessel. A pressure vessel is a sealable stainless steel vessel that can withstand high pressures. The drug product is placed inside, and the vessel will have a dip near the bottom of the barrel to collect as much solution as possible when the surface level drops at the end of a fill. Here, there is a dip tube to pull the solution into the filling line. The vessel is sealed and then pressurized with the gas from 10 to 100 psi, depending on the project. The gas can be sterile air or sterile nitrogen for oxygen-sensitive products, and this pressure provides the push to get the solution through the tubing. Since this system involves a lot of pressure, we need to ensure we do not overstress the system. Overstressing the system can cause a leak or a break in the line, which can result in product loss, sterility risks, and especially a safety concern. As a result, we have to use pressure-rated tubing for the inlet tubing that is rated for the maximum pressure that the system can withstand. This could be reinforced tubing that is threaded to prevent bulging, or rigid tubing that uses PTFE instead of soft silicone. Typically, we use reinforced tubing. Once the solution leaves the piston pump, the pressure on the system drops completely, and we are now only concerned with selecting the right tubing to ensure we are getting accurate fill volumes each time we dispense the solution. If we were to use the soft silicone tubing that we use for a typical fill, then the tubing is at risk of bulging at each pump of the piston pump. It is difficult to push highly viscous solution through the tubing, and some of that stress may instead push outwards on the wall of the tubing. Bulging poses a problem with accurate dispense volumes because it takes time for soft silicone tubing to relax back to its normal position when it does bulge. As the tubing relaxes, it presses the solution in the tubing out of the fill needle, and this can lead to dribble. So, the fill needle will dispense some of the volume, but the remaining volume will dribble out of the fill needle after it dispenses. This can cause variable fill volumes and it can lead to spilling on the outside of the containers if the fill needle continues to dribble as the XY table or conveyor belt moves to position the next container under the needle. To prevent bulging, we need to select tubing that is fortified enough that it maintains the same inner diameter during these moments of pressure when the pump is pushing viscous product through it. For this reason, we always select rigid tubing. Most clients opt to fill in syringes if they have a highly viscous fill, and all of our filling lines have the capability to process these containers, and each filling line has a piston pump option, but we can also fill in cartridges or vials on these lines. Overall, our setup for a semi-viscous solution, generally 100 to 1000 centipoise, is a bag or glass vessel, fortified or rigid tubing that leads into a piston pump, or rigid tubing leading to the fill needle. For highly viscous solutions, greater than 1000 centipoise as a rule of thumb, we use either a pressure vessel that is pressurized with sterile air or nitrogen, fortified or rigid tubing that leads into a piston pump, or rigid tubing leading to the fill needle. This is the technique used for filling most viscous solutions. Now that we have discussed filling, let's work backwards and look at sterile filtration. When you're preparing a sterile viscous solution, you have three options. First, you can fill the product and terminally sterilize it in its final container. If this is possible to do with your product, then it is required to be done. However, most products we work with cannot withstand the energy of terminal sterilization, whether it is heat or gamma radiation, so you are left with two other options. You can sterile filter your viscous drug product, and if that is not possible, then you can aseptically formulate your product. This is where you prepare your drug product solution with sterile ingredients within an isolator. We have worked on projects like this before. The real challenge with sterilizing viscous drug products is moving the solution through the tubing and sterile filter. If it is exceptionally long to perform sterile filtration with a peristaltic pump moving the solution, or if it is ineffective to use this type of pump, then our solution to address this problem is, yet again, we will use a pressure filter. Of course, when we use a pressure vessel, we must follow it with pressure-rated tubing, either rigid or reinforced. It doesn't matter. These are connected to the filters. A normal filter usually works, but if we have a hard time filtering a product and it requires extra force to move it through, then we may use stainless steel filter holdings. Once the product is filtered, it will exit through tubing. Typically, this is pressure-rated tubing for good measure, and it enters our choice of vessel. More often than not, this is another pressure vessel, but if the product is only slightly viscous, anywhere from 100 centipoise to 1000 centipoise, then the product may be able to be filled from a bag or glass vessel. One thing we have to consider when filtering a highly viscous drug product is line loss. If the client is concerned about product loss, then a formulation chemist can help reduce line loss by massaging the tubing to remove any remaining solution trapped in the outlet of the filtration assembly. This can't be done with viscous products. The tubing is reinforced, and the product is viscous, both of which makes it far more difficult to physically press the solution out by massaging the tubing. So, to limit line losses during sterile filtration, we cut the outlet tubing to as small of a length as possible, or we can attach the filter directly to the sterile vessel. After this, the pressure vessel is connected to the filling line and we can begin filling.
Ben, thanks so much for your help. I do have CEO Shawn Kinney to speak about how we determine equipment and process requirements and other considerations. But first, Shawn, I just want to mention that you have a lot of experience in viscous filling. Could you tell us a little bit about your background first?
Of course. In the early 1980s, I was a manufacturing operator filling viscous hyaluronic acid solutions into syringes for ophthalmic indications. I ultimately became the vice president of operations for that company, overseeing the formulation and filling of millions of units of viscous hyaluronic acid for ophthalmic and orthopedic uses. From there, I started a CMO in the Boston area that specialized in filling viscous drug products and patented bubble-free filling, a technology that was very important in viscous product filling. At that company, we filled many different viscous products into a variety of containers. One polymer solution was so viscous that it could be cut with a knife and maintained its shape for several minutes. That company would ultimately become part of a larger CMO.
Thanks, Shawn. So given all that, you should be able to tell us how to determine what equipment, what process requirements, and what approach to take for a new viscous fill.
Yes, certainly. Let's start with formulation. The client should be able to inform us if their product can be terminally sterilized. If it can, great, because that makes the formulation and filling processes considerably easier. In this case, the product is formulated in a clean, non-sterile, and non-sealed vessel. It may be filtered to remove particulates if present and possibly to reduce bioburden. Depending upon the viscosity, the product may be filled from the formulation vessel, or if necessary, it may be transferred to a vessel that can be pressurized. Once the product is filled and sealed, the drug product will be terminally sterilized in its final container. If the product cannot be terminally sterilized, which is often the case, then we move to determine if we can sterile filter the product. As Ben described, a typical sterile filtration setup for highly viscous drug products is to formulate the product in a pressure vessel. The vessel is sealed, and compressed air or nitrogen is used with pressure-rated tubing to push the product through the sterile filters. The filters are connected to a pressure-rated sterile receiving vessel, a pressure vessel, from which the product will be filled. It's best practice to use pressure-rated tubing between the redundant filters and the outlet of the filter to the receiving vessel. To determine the sterile filtration setup, we perform several filter studies to determine how effectively the solution can move through the filter. Some products filter easily and may require only a few pounds of pressure to complete the filtration. However, some products may require pressures up to 100 psi or higher and large surface area filters to complete the filtration in an acceptable time. It may be necessary to find filters and specialty housings that are rated for very high pressures. In one application, we had to use 24-inch diameter flat filter membranes and stainless steel housings to achieve a pressure of 200 psi to get a reasonable filtration rate. When working with gas pressures that are above the bubble point of the filter, extreme caution must be exercised. The flow of the product needs to be stopped before the gas reaches the surface of the filter to prevent a very large rush of the gas through the filter into the receiving tank. Using any pressurized gas, safety must be considered. Appropriate pressure-rated tubing, filter housings, fittings, and connections must be used. Pressure relief valves should be included on all tanks. Receiving vessels should be open or have appropriate vent filters to avoid building up pressure inside the vessel during the filtration or transfer from one vessel to another. The pressure will be very low on the outlet side of the filter when product is flowing through the filter, and vessels such as glass bottles or stainless steel tanks can be used as receiving vessels as long as they have an opening such as a vent filter to let gas out as the vessel fills. If using an inflatable container such as a bio bag, a vent filter may not be necessary. As mentioned earlier, however, if you use a pressure above the bubble point of the filter, product flow should be stopped before the gas reaches the filter. For viscous products that cannot be sterile filtered or terminally sterilized, they may need to be aseptically formulated. In these cases, the viscosity-enabling ingredients are generally gamma or electron beam sterilized and aseptically formulated with liquid products being sterile filtered. Let's talk about sterile filling because that is one of the more difficult processes to optimize. We are going to discuss how to determine if a product requires a pressure vessel and/or a piston pump. If the product does require a pressure vessel, what pressure is required? And how do you reduce overall stress on the system? We will also talk about aspects that will affect your fill, such as gas bubbles in solution. These can be a real problem in filling, and we will discuss why. Newtonian versus non-Newtonian liquids. Before we start, I have a few words about tubing on the inlet and outlet sides of the pump. Whether you are using a peristaltic or piston pump, we prefer rigid FEP or PTFE tubing on the outlet side of the pump, since rigid tubing will not expand and collapse during pumping. This leads to more accurate fill volumes and minimizes problems with dripping from the filling needle. On the inlet side of the pump from the filling vessel, any tubing is fine as long as it is compatible with the product, can withstand the pressures being applied to the inlet side, and should be of the largest diameter possible. It is our preference to use a peristaltic filling process if possible, because it is easy to set up and is less expensive than using stainless steel piston pumps. With less viscous products, we will attempt to fill with no back pressure on the inlet side of the pump, making the line from the filling vessel to the pump as short as possible with the largest ID tubing reasonably possible. We perform filling studies to evaluate the amount of product delivered from the pump at various pump speeds. As the pump speed is increased, eventually a point will be reached where the amount of product delivered in a dose starts to decrease because the product is not flowing into the pump fast enough to fill each segment of the tubing before the roller pinches off the next segment. The speed of the pump and the delivered dose can be graphed to get something that looks like this. As you can see, when the pump is at lower speeds, the weight checks stay consistent. Once the pump begins to move faster than the viscous solution can refill the pump, you'll see the weight checks start to drop off. The maximum pump speed is the last pump speed at which no loss of delivered dose was observed. If this pump speed is reasonably fast enough to allow filling operations at an acceptable rate, then these are the conditions to use. If the pump speed is not fast enough for filling, a pressure vessel will be required. The experiment just described can be repeated using a pressure vessel with just a few pounds of pressure in the vessel. If an acceptable filling speed is found, then these conditions should be used for filling. If this still results in unacceptably slow filling, higher pressure in the filling vessel and the piston pumps are required. If a piston pump is required, the similar fill study will be repeated using a piston pump instead of a peristaltic pump. Piston pumps have 3 speeds that can be programmed: the suction speed, the speed at which the pump runs during the intake stroke; the rotation speed, the speed at which the piston rotates between outlet and inlet; and the fill speed, the speed at which the pump expels the product. The suction speed is the most important speed for optimizing piston pump filling. If the suction speed is too fast for the given pressure on the filling vessel, the pump does not fill all the way. The piston retracts up to suck the product in, but if the product cannot flow in fast enough, the pump will have completed its intake stroke and turned to the outtake stroke with a vacuum inside the pump. On the outstroke, you will observe that the stroke starts, but no product is expelled from the fill needle right away. The piston first has to move down to compress the vacuum before it starts to push product out of the pump. The suction speed is essentially set at a speed that will yield a reasonable filling rate. This is often 25% to begin with, and the pressure is set to a value which experience has shown is effective for the viscosity of the product. Several doses will be collected, and they will each be weighed. Then the pressure is increased in increments of 5 psi, and another set of doses will be taken and weighed. This process will continue until the average weight of the doses does not increase any further. It is important to choose the lowest pressure that will allow us to pump the solution at a sufficient speed. What is a sufficient speed? Well, that depends upon the lot size and the desired speed that we want to fill it. The longer the filling operation, the greater the likelihood that a problem could arise. Longer fills pose a greater threat to sterility, though the risk is low when filling in isolators like we do at PSM. If the product is temperature sensitive, we have to keep this in mind. As a CMO, we always want to keep filling time as short as reasonably possible because it improves our capacity and minimizes charges to the customer. Let's talk about stress quickly. There are several ways to reduce stress on the system. One way we reduce stress is to keep tubing lengths as short as possible and the cross-sectional area or inner diameter as large as possible to reduce the pressure drop. That is, the loss of pressure from the outlet of the tank to the inlet of the pump. For example, if the pressure vessel were set to 50 psi and the pressure on the solution when it reaches the piston pump is only 10 psi, then the pressure dropped 40 psi. If we need 10 psi pressure to effectively push the solution into the pump, then we must set our pressure vessel at 50 psi. However, if we were to reduce the length of the tubing and increase the internal diameter, suddenly there is less resistance to move the solution through the tubing. Maybe then pressure would only drop 20 psi instead of 40, and then we can set our pressure vessel to 30 psi to get the 10 psi pressure needed to move the solution into the pump. Our pressure vessels can reach up to 100 psi, but we like to keep it as far below that as possible for safety reasons. Okay, now that we have figured out how we are going to filter and fill your product, let's discuss some other factors that will affect your fill. Bubbles, the bane of viscous filling. Air inside filling lines is a real problem when performing viscous filling. If an air bubble started in the pressure vessel, it would be small up to the outlet of the piston pump because the pressure in the vessel and the filling line is compressing it. Gases are compressible, liquids are not. Once the bubble exits the pump, the pressure on it drops significantly and the air bubble will expand. This can cause dripping and dribble because the bubble will take some time to expand in the viscous product as the product is being expelled through the filling needle. The bubble also displaces product, and it results in variable fill volumes. Getting bubbles out of a viscous solution is challenging, so it is very important to be careful when mixing a viscous product, such that bubbles are not created in the solution. If bubbles do appear, there are a few options to mitigate the problem. If the solution is only slightly viscous, then one can wait and allow the air bubbles time to reach the surface of the solution. If the product is extremely viscous, waiting for bubbles to rise may take too long. One solution is to pull a vacuum on the product to help pull the bubbles out of the solution. Very viscous products are typically formulated and filled into a pressure vessel. In this case, it would be relatively easy to seal the container and pull a vacuum. Some pressure vessels have mixing shafts built into them, and mixing the solution while pulling the vacuum has helped remove bubbles. Okay, let's discuss another factor, Newtonian versus non-Newtonian fluids. A Newtonian fluid is one where the viscosity remains the same regardless of the amount of shear applied to it. Shear force is a force that is parallel to and on the top of a surface or cross-section of a body. When we discuss shear force with fluids, we can think of the shear force in tubing. As solution moves through tubing, there will be a friction or a shear force acting on the solution in the opposite direction that the solution is moving, along the inner surface of the tubing. And so the solution will actually move much faster in the center of the tubing than it will at the edges. This is similar to a river, where the water moves faster in the center of the river, where it is deeper than it does at the edges of the river. If we look at a cross-sectional diagram of a solution moving through tubing, this is what the inner velocities look like. The shear force is subjected on the fluid by the inner surface of the tubing. Newtonian fluids will have the same viscosity when moving through this tubing, regardless of how quickly it is moving. You will need the same force to keep the solution moving as you will need to get the solution to start moving. Non-Newtonian solutions do not follow Newton's law of viscosity. This means its viscosity changes depending upon the force it experiences. Hyaluronic acid is a good example of a non-Newtonian solution. When you move a solution of hyaluronic acid through tubing, a shear force subjected on the HA solution causes the viscosity of the solution to drop. It thereby takes less force to move the HA at that viscosity than is required to get the solution to start moving. The reason for this, at least for HA, is the product is made up of many long polymers. These polymers exist in solution as coiled, entangled molecules. When these entangled molecules are subjected to a shear force, the adjacent velocities will pull on the coils at different speeds, and this helps to pull the polymers out of entangled clumps and into long strings oriented in the direction of flow. This makes it much easier for the polymers to move. This is shear thinning. There are also solutions that are shear thickening, though they are less common. A good example of this is cornstarch and water. If you were to stir this solution slowly, it looks milky and thin, but if you vigorously stir it, it becomes much more viscous. We more often work with polymers that shear thin. This makes the production easier since it is easier to mix the drug product once you get the mixer started. It will move much easier. It also puts less stress on the filling system. The pressure drop from the pressure vessel to the piston pump is smaller, which allows us to set the pressure vessel to a lower PSI to fill effectively. We have worked with solutions that shear thicken, but we would have to mix and fill very slowly for those products since the viscosity would increase as the velocity and shear forces increase. At this point, we have covered everything that we were planning to. Thank you all for joining, and I hope you learned a lot from this presentation.
Thank you, Shawn. That concludes today's presentation. In just a moment, we will transition to the Q&A portion of the webinar. Again, to ask a question, select the word bubble that appears in the toolbar at the right-hand side of your screen. An area to type in your question will appear. Write us your question and click send, and we'll display those for our speakers to answer. As part of today's event, you can also download the slide deck. And I'm going to give everyone a moment to ask their questions right now. Today's webinar is the fourth webinar of the series, Sterile Filling 101. All of our upcoming events are listed here, and recordings of previous webinars are also available both on our website and YouTube page. In October, we will be airing our next webinar regarding reducing loss in fill finish for high-value drug products, and we'll discuss solutions to reduce volume loss, including a few risky solutions that should be avoided. Following the end of this event, I will be sending you an email with a sign-up link to each of these events, but you can also go directly to berkshiresterilmanufacturing.com/sterilefilling101 to register to those events. Okay, it looks like we've received all the questions we're going to get. So let's start with that first question. This one will be going to Shawn. And the question is, can a solution be too viscous to fill and filter?
There really are no products that are too viscous to fill, but it will require, as viscosity increases, more sophisticated equipment, slower processes, and greater expense to complete the filling operations.
Thank you, Shawn. I have another question for you. The question is, if you did have bubbles appear during formulation, wouldn't they be filtered out?
If you have bubbles appear during formulation and you're sterile filtering your product, you can certainly get the bubbles removed by the filtration process as long as you are below the bubble point of the filter, the pressure, that is, of the pressure vessel. And those bubbles would accumulate on the non-sterile side of the filter, and then you could remove them with the vent on the filter. However, if you have a product that you have to aseptically fill or aseptically formulate, having bubbles during the formulation would be a problem. You'd have to find another means to remove those before you go on to into filling.
Thanks, Shawn. That was well said. I have another question. This is going to go to Ben. Ben, how do you fill for a product that needs to be recirculated?
For something that needs to be recirculated, typically we'll take the filling vessel and we'll put a length of tubing on the outlet of it, and we'll pump back into the vessel using a peristaltic pump. That's just to keep the solution moving throughout the fill. And viscosity isn't really a concern with this because we are still able to pump with a peristaltic pump. It's just not very fast. There might be some back pressure on it, but we're still able to get solution to move. And since all we're concerned about is that the solution is moving, then we use a peristaltic pump for that.
Thank you, Ben. I have another question for you. What ID fill needle is used in a highly viscous fill?
So typically we will use a larger inner diameter fill needle than we would typically use for a fill when it comes to viscous products, but it depends on a lot of factors. It depends on the volume we're filling, the viscosity of what we're filling, the precision we need to hit for that fill, because all those things can be variable for any project. I'm working on a project right now where it's a 2 milliliter fill. And for that, typically we would use like a 1.5 millimeter fill needle, but we size that up to a 3 millimeter fill needle to help alleviate some of the issues we've seen because of the viscosity of the product.
Thank you, Ben. I have one more question. I'm going to direct this towards Shawn. Can you use a pressure vessel with a peristaltic pump?
Certainly, you can use a pressure vessel with a peristaltic pump. You won't be able to use it at a very high pressure because the tubing inside the peristaltic pump is rated lower than the pressure that you could apply to the pressure vessel.
Thank you, Shawn. That was well said. We will end on that question. I want to give a huge thank you to everyone here that joined today's webinar, and a thank you to our speakers, Dr. Shawn Kinney and Ben Callan. To all of our viewers, keep your eye out for my email. And don't forget to sign up for our other webinars, which you can do by going to berkshiresterilmanufacturing.com/sterilefilling101. I hope you took a lot away from this presentation, and I hope to see you again in our future webinars.